What if I told you you're standing inside a time machine right now? No buttons, no sci-fi, just physics. Right now, as you watch this, your body contains atoms older than Earth by billions of years, and your phone is catching signals that began their journey inside a star. And the wildest part is that one of Brian Cox's favorite space facts says the most important number in the universe might be something like 0.00001. Stay with me, because that tiny number may decide whether anything, stars, planets, life, gets to exist at all. Here's where it gets crazy. If the sun were the size of a front door, Earth would be a peppercorn about 15 meters away. But the nearest star in that same model wouldn't be down the street. You'd have to place it thousands of kilometers away, across a continent, just to get the spacing right. And that's still only our local patch. The Milky Way contains hundreds of billions of stars, and beyond it are more galaxies than you can comfortably picture without your brain quietly refusing. At the same time, the universe produces objects so extreme they feel like glitches. Pulsars, spinning neutron stars, can keep time with a stability that rivals the best clocks humans have built. And despite all that grandeur, space is so empty that if you removed the emptiness inside atoms, if you squeezed out the space between nuclei and electrons, the entire human species could fit into something the size of a sugar cube. So why does anything feel solid? Why do you stick together? And why do scientists keep arguing about the most basic ingredient of the cosmos? Nothing. To understand why this is strange, you have to start with the normal story. Gravity gathers gas, gas collapses, pressure rises, fusion ignites, stars shine by turning hydrogen into helium, releasing light and heat. Planets form from leftover dust. Chemistry stacks complexity onto complexity until one small world produces creatures capable of looking up and asking what's going on. In that picture, gravity is the patient sculptor. It pulls matter together, builds stars, builds galaxies, and over cosmic time, it should slow the expansion of the universe down, like a thrown ball losing speed as it climbs. Then we discovered two key truths. First, the universe is expanding, space itself stretching. Second, light takes time to travel, so when you look far away, you're looking back in time. Astronomy is literally time travel, but with photons instead of machines. And this is where things get strange, because when we measure how the universe expands today, it doesn't behave like a universe filled only with matter and gravity. The expansion is accelerating, as if there's a gentle, relentless push built into space itself. We gave that push a name, dark energy. Not because it's spooky, because we don't know what it is. One of the most unsettling parts of modern cosmology is that this isn't a vibe or a guess. It's anchored in data. In the late 1990s, two groups, the Supernova Cosmology Project and the High Z Supernova Search Team, used Type Ia supernovae as standard candles. These stellar explosions have a consistent intrinsic brightness, so if one looks dimmer, it's farther away. The expectation was simple. Gravity should slow expansion, so distant supernovae should appear a certain way. But the supernovae were dimmer than expected, farther than expected, meaning the universe had expanded more than it should have. The only clean way to explain it was that expansion has been speeding up. That discovery helped earn the 2011 Nobel Prize in Physics. The universe really is doing that. Now zoom back into another Brian Cox favorite. You are made of star ash. Hydrogen is ancient, born early in the universe, but the carbon in your cells, the oxygen you breathe, the iron in your blood, those are forged in stars and scattered into space when stars die. The atoms in you have been recycled through stellar generations. You are not a visitor in the universe. You're what the universe does when it has time and chemistry and starlight. And now we collide those comforting facts with the one that makes people uneasy. The emptiness of space isn't empty. Quantum physics tells us that nothing is restless. Even a perfect vacuum has fluctuations, temporary ripples of energy permitted by uncertainty. So the obvious question becomes unavoidable. If empty space has energy, could that be the push? Could vacuum energy be dark energy? That's where the mystery turns from fascinating to almost absurd. Because when physicists do the straightforward calculation, adding up the expected vacuum energy from quantum fields, the answer doesn't come out slightly wrong. It comes out catastrophically wrong. Depending on how you frame it, the mismatch between what theory naively suggests and what astronomy observes is on the order of 10 more 20. That's not a rounding error. That's one of the largest known disagreements between our equations and reality. And yet the observations keep insisting on something else. The vacuum energy, if it's there, is tiny, but not zero. So here's the best explanation that is both satisfying and unsettling. Dark energy might be a cosmological constant, a built-in energy of space itself, constant in time and uniform in space. Picture space like a rubber sheet. Matter makes dents in it, gravity. But dark energy is like the sheet having an inherent tendency to stretch. The more sheet you have, the more stretching you get. That's why acceleration only becomes dominant when the universe gets old and spread out, when matter is diluted and the quiet push of the vacuum starts to win. Now we return to that ridiculous tiny number from the beginning. In plain language, it's the scale of the observed dark energy compared with the natural scales that particle physics would lead you to expect. It's so small it looks tuned, like it's been delicately set to a value that allows structure to form. Because if dark energy were much larger, the universe would have accelerated too early. Matter would have been pulled apart before it could assemble into galaxies. No galaxies means no stars. No stars means no planets. No planets means no life to ask the question. The universe seems to sit on a knife edge. Enough dark energy to accelerate expansion, not enough to erase the cosmic architecture that makes observers possible. But just when you think you've got a handle on it, there's a second twist. Because cosmological constant isn't the only story that can fit the sky. Scientists debate at least 3 broad possibilities, and each one is strange in a different way. Possibility 1, it really is a constant. Simple, elegant, but it leaves the why so small problem staring at you, unsolved. Possibility 2, quintessence, a dynamic field. Instead of being a fixed number, dark energy could be something that evolves, like a slow-rolling landscape whose value changes as the universe ages. That would mean the acceleration isn't a permanent feature, it's a phase, and the universe's fate depends on how that field behaves in the deep future. Possibility 3, modified gravity. Maybe there isn't a new energy component at all. Maybe gravity behaves differently on the largest scales, and Einstein's equations need a correction when you zoom out far enough. In that case, dark energy would be a signpost pointing not to a new stuff, but to new rules. And the tension doesn't stay philosophical. It shows up in measurements. Different ways of measuring how fast the universe is expanding have produced persistent disagreements, often discussed as the Hubble tension. Is it hidden systematic error? Is it new physics? Or is it the universe nudging us, again, to admit that our neat story is missing a chapter? That's what makes this so personal and so cosmic at the same time. In the standard picture of cosmology, the thing we understand least is not a tiny corner case. It's dominant. Something like 70% of the universe's energy budget is attributed to this dark energy component. The majority of reality, by our best accounting, is an unknown that only reveals itself through the way it stretches space. And the consequences are enormous. If dark energy is constant, the universe expands forever, and over unimaginable timescales, distant galaxies drift beyond reach, their light stretched and thinned until the cosmos grows quieter and lonelier from any single vantage point. If dark energy evolves, the future could look radically different: slower acceleration, faster acceleration, or exotic endings that depend on the model. If gravity itself needs rewriting, then that change ripples outward into how we interpret black holes, gravitational waves, the formation of galaxies, everything. The hopeful part is that this mystery is not untouchable. It's measurable. Scientists are mapping billions of galaxies to see how cosmic structure grows. They're using gravitational lensing, nature's own magnifying glass, to track invisible mass. They're refining supernova surveys to sharpen the distance ladder. They're cross-checking with the leftover light from the early universe. This isn't guessing in the dark, it's building traps for reality, setting up tests that can rule ideas out. And that's the Brian Cox-style wonder hiding in the discomfort. The universe doesn't just allow us to ask these questions, it leaves clues. Your atoms carry the history of dead stars. The light in the sky is a record of time. The expansion of space itself is a message about the deepest laws of physics. Empty space, nothing, might be the most powerful actor in the cosmos, quietly deciding the fate of everything that will ever exist. So when you look up tonight, you're not just seeing stars, you're seeing a balance, gravity pulling inward, dark energy pushing outward, and the entire future of the universe balanced on a number so small it looks impossible. And somehow, against all intuitive expectation, that impossibility is exactly what made it possible for you to be here to notice.